Hello, and welcome back. Mr. Wakefield here, looking at the third and final part of section 1.6, and we have these equations here that are called quadratic in form. That means that they are not officially quadratic, but we can transform them through this thing called a substitution to make them look like they're quadratic. Let's go ahead and take a look at this first example here. Just want to tell you, I know it kind of looks like it's quadratic right at the beginning, but it's not. Remember, a quadratic equation, similar to this one right here, which we'll talk about in a minute. It's when you have a polynomial on both sides and the highest exponent attached to the variable is 2. Okay, but in order to be a polynomial on each side in the first place, need to remind you that a polynomial cannot have negative exponents. It's got to have whole number exponents like 0, 1, 2, 3, 4, those kinds of numbers for their exponents. And so you can't have negative exponents. You also can't have fraction exponents like this one here, 2/3 and 1/3. And you also can't have, as I just said, you can't have an exponent higher than 2 like this one right here is 4. And it's attached to a bracket that has a variable in it. So that can't possibly be a quadratic equation either. Okay. And so what we're going to do with these three equations down here, just like I did here in this first example, which I'll let you look at, I'll kind of refer to it briefly here. But what we're going to do is convert each one of these three equations into a quadratic equation, because we know how to solve quadratic equations now, and then we can once we convert it, we'll be able to go from there. Real briefly here, what I did here was I converted this into this quadratic equation. I solved it. Okay, I did it by factoring. Doesn't mean you always have to do it that way. This is another one of those problems where when you end up with a quadratic equation a few steps into the problem, just like before, it'll be your choice of which method you want to use to solve the quadratic equation, because there's nothing here that says that you have to use one particular method over another. Okay, so it's your choice here, just so long as you're able to solve it and show your work, of course. Once you do that, though, you need to go back and to solve for the original variable. You can't just say, hey, I got u by itself. I got the variable by itself. I'm done. Normally, that would be okay when you're solving a one-variable equation, but because the original variable was x and not u, we then need to go back and substitute again. And again, I'll explain all that, okay, as we go through each problem here. So what we need to do is we need to figure out what the substitution is for each problem. Notice that when you have a quadratic equation, all right, you have a variable squared, obviously. You don't necessarily always have to have the variable of the first power, but in these problems we will. It's just the way it works out. And so what you need to do in each one of these three problems is you need to find something that you can replace with the letter u, okay, substitute with the letter u in other words, and then something also that will be u squared. I'll explain that carefully here, okay. Basically, what's going to happen in all three of these problems, and your homework problems should come out similar as well when you do them, is that there's going to be something in the middle of the equation which can serve as your u, okay? In other words, it'll be equal to u. It'll be a good choice for you. And again, I won't be able to, part of the problem is for you to figure that out yourself. It's not going to be told to you what the u is, but the good news is that all these problems are very similar, where the u that you need to choose will be somewhere right around the middle of the equation, okay? And remember, you need a u squared as well. Well, the u squared will usually be somewhere near the front. Not necessarily completely in the front, but somewhere near the front. Okay, let me show you what I'm getting at here. Notice here that u, if you square u, it's equal to u squared, right? Okay, if I have the letter u, all right, and I want to square it, it's going to be equal to u squared, right? Let me zoom in there for you. Okay. So in a similar way, if I choose a particular thing in the equation to be my u, to be equal to u, I need it to be something that when I square it, that thing will also be in the equation, so that I'll have my u squared as well. Remember, we need a u and a u squared in the equation. So here's the thing. What if I choose this thing right here? to be my u. Why would I choose that? I would choose that because if I square that, okay, let me give myself a little bit more room here. Okay. So if I choose that, then what would u squared be equal to? If u was equal to x to the negative 1, then wouldn't x squared be equal to, I'm sorry, u squared. Wouldn't u squared be equal to x to the negative 1 squared? Because if u and x to the negative 1 are the same, then if you square u, you're also squaring x to the negative 1. By the way, what is this equal to? Well, just a little review here, all right? When you have something taken to a power inside of a bracket, just those two things, the thing taken to the power, the x and the exponent, and then you have a bracket around it, and then you have another exponent on the outside, that's the same thing as multiplying the exponents if you wanted to get rid of the exponents there. Okay, you can see an example of that from the prerequisite review packet in the exponent rule portion of that, where it says exponent rules at the top. See how I 4 and 2 there, and it becomes 8 because you're supposed to multiply in that case when it looks like that. In the same way, this would be negative 1 times 2, so it's going to be x to the x stays the same, but the exponents become negative 2. Hey, isn't that, wait a minute, that is over here, isn't it? Okay. Remember what I just said, we want to have something, we want to pick something to be our u, we want to pick something to be equal to u so that when I square it, in other words, when I figure out what u squared is, it's also going to be in the problem, okay? Watch what happens now that I've done that. Okay, the x negative 2 is now the same thing as u squared. So I can substitute the x negative 2, I can replace that, in other words, substitute, replace, same thing. I can replace that with u squared since it's the same thing as u squared. I'm just using color here just to make it, just to emphasize certain things. You don't have to use color here. You can just use your pencil. But then bring down the plus. Notice the 20 stayed the same there. I'm just looking at the u and the u squared here and what they're equal to. Since the u is equal to x negative 1, not the 9, so the 9 is separate, but the x negative 1 then can be replaced by the u, since u and x negative 1 are the same thing. Okay, now why would I want to replace it with the u? It's because it now looks like a quadratic equation. Okay, and it needs to be a one-variable quadratic equation, so you need to get rid of the x's on this step and just have u's in there. U should be your only letter in there, your only variable. Okay, so that's a strategy that you can take and you need to take in order to make it look like a quadratic equation. Now, I'll go ahead and solve this in just a moment, but I know some of you are probably thinking, wow, I'm still trying to get used to this whole idea. I get that. So let's practice that first step again on these other problems before we come back and finish up each problem, okay? Let's try it on number 2 now, and then we'll come back and solve each problem. Once again, remember I said that your u that you want to choose is usually going to be somewhere in the middle of the problem, but it has to be something that when you square it, it will be equal to something that's somewhere near the front of the problem, so that when you do these substitutions or replacements, it will then look like a problem that just has u in it, and it'll look like a quadratic equation. Can you see here that if I take this right here, and maybe you can't see it yet, so I'll help you, but notice that if I choose that right there, okay, let me just write it down. If I choose that, what would u squared be equal to? Remember, we want to choose u so that when we figure out what u squared is equal to, like we did over here, it will then be equal to something that's somewhere near the front of the problem. Well, if I square this whole thing right here, and I'll use another bracket here to indicate that I'm squaring the whole thing. Again, this also works with brackets. If you have a bracket taken to a power inside of a bigger bracket, and then another exponent on the outside, it works the same way as right here where you multiply the exponents. And then the thing that was taken to that power on the inside of the bracket, that thing stays the same. Okay, so just like the x stayed the same here, the 2x minus 1, which is inside the bigger bracket, that stays the same. And then you multiply 1/3 times 2. 1/3 times 2 is what? Okay, that's the same thing as 1/3 times 2 over 1. And that would be 2/3, isn't it? 1 times 2 and 3 times 1, 2/3. Well, hey, check it out, you guys. The bracket to the 2/3 power, that's in the front. Okay, and so that can then be replaced by u squared, since we just found out that u squared is the same thing as that. And so this big thing right here, which is the same as this over here, that because it's the same thing and because it's equal to u squared, this first red box can then be replaced by u squared. There's nothing, notice there's nothing in front of it, so you're not going to have like a 20 in front of it like you did on this problem. There's nothing in front of it this time. Okay, so you got u squared, you bring down the plus 2. Okay, we're just replacing the things that I boxed in here because it's the things that we boxed in that are equal to u and u squared up here. So then this second box here, we found out that that was equal to u. Actually, we chose that, but it is equal to u, and so that becomes u. We replace this second box with u, and then the rest of it, again, has nothing to do with u and u squared, so that just stays the same. Bring down the minus 3, that stays the same. Bring down the equal to 0 as well. So once again, you can see that this now looks exactly like a quadratic equation. Okay, let's do it one more time, and then we'll start solving these problems. Notice here that if I choose this thing, okay, to be my u, if I choose that thing to be my u, I'll write it down right here. Very similar to problem number 2. Okay, if I want to figure out what u squared is equal to, that would be, again, you have a bracket taken to a power, and then you want to take that entire thing to the second power. Okay, just like we did here where we took that entire thing to the second power. All right, what happens? When you have a bracket taken to a power inside of a bigger bracket, and then you have another exponent on the outside, what happens is that bracket on the inside stays the same, just like the 2x minus 1 did. Okay, and then the 2 and the 2 get multiplied together to equal 4. Okay, and so there we go. And so not a coincidence, you guys, that u squared then is equal to this, but that, the x minus 4 to the 4th power, that's right here. And so now you can replace this box with u, and you can replace this box with u squared because this box is equal to u squared, as you can see here. So let's do that. The 8 stays the same. The minus 10 stays the same. The equal to negative 3 stays the same. It's just the boxes that get replaced with u and u squared because those boxes are equal to u and u squared. So the first box is equal to u squared, as we can see here. Bring down the minus 10. The second box is equal to u, so we replace it with u. Okay. And then equal to negative 3, we bring that down. And once again, same thing is true for all 3 problems, you guys. After you do your substitutions, you figure out what u is and u squared, and you do your replacements, your substitutions. In other words, you end up with quadratic equations on all 3. So just like we did up here in this example, after we write down the new quadratic equation with the u in there, no x anymore, we then solve that equation, okay, and then we'll go from there, okay? So let's do that. Okay, so let's go ahead and start solving these things. All right, again, these are quadratic equations, so you have your choice here since the problem doesn't say you have to use a particular method. We have 4 different methods for solving quadratics, okay? Each one of these look like the kind of problem where you'd move all the terms to one side and then try to factor it. If the factoring doesn't work, then you can try to do the quadratic formula. Okay, in the first 2 problems, everything is already moved to one side. In fact, when you have a u squared and a u and then a term that doesn't have u at all, you want it to be in that order. You want the u squared term to be positive. All that's true here. All that's true here as well. And all of that, that's also true here if you move over to the 3, okay, and you write it out like this, okay. So we're on our way here, you guys. We just have to solve these, okay. Let's start out with this one. If I factor that, doing the Berry method, I get 20 times 1 is 20. All right. And what adds up to 9 in the middle out of the factors of 20? It would be 4 and 5. And so that means I'm going to have 20u plus 4, 20u plus 5. But remember, you got to do that last step of the Berry method where you have to factor out the greatest common factor out of each bracket and then discard those GCFs in the last step of the Berry method. Here the GCF is 4. If I factor that out, it would be 5u plus 1. If I factor out the GCF here, which is 5, it would be 4u plus 1. And there we go. Okay. Then I have 2 factors here. We've factored this left side of the equation completely. It doesn't factor anymore. And we get what? We get setting both of these equal to 0 like we normally do at this step. And then we solve for u. What do we get? Well, we need to move the 1 over since these are linear equations now on this step. Again, this is all the stuff we saw in 1.4 and a little bit in the earlier part of this chapter as well. If we divide out the 5 here and the 4 here, we've got what 2 answers here? We've got negative 1/5 and negative 1/4. Okay, but remember what I said at the beginning of the video. You need to solve for the original variable. You can't say, hey, I solved for the variable, I'm done. This is not the variable you're supposed to solve for ultimately. Yes, you're supposed to solve for u at first, but there's still more that needs to be done. I took the u, I took what it was equal to, and ironically, it's the same as the actual problem we're doing right now. It's x negative 1, and I put the x negative 1 back in where the u was located. So it's like you're back substituting. Let me show you how that works. Okay, so since u is equal to negative 1 in this problem, what you do after you get u by itself, and please wait until you get u by itself first. But once you do, then you replace the u with the x negative 1 because that's what it's equal to in this problem. And now you solve for x. Now you might be wondering, how do I solve for x when it's got a negative exponent? Remember, when you have, again, a little bit of review here. When you have this is back in that exponent rules section again of the prerequisite review packet. When you have something taken to a negative power, what you do is you take a 1 and then put that same thing underneath the 1, but you change the negative to a positive. Let me zoom in there a little bit closer. So let's do that here in this problem. X to the negative 1 would be 1 over x to the first. Because the negative 1 becomes a 1, the x would stay the same just like the a does here. And so x to the negative 1 becomes 1 over x. Same thing here. Okay. Sorry about that. There it is. Okay. And so x to the negative 1 becomes 1 over x. Now we can solve these fraction equations that we've just created here. Okay, we've learned how to do that, but there's a easier way to do it than that method I showed you in the earlier part of this section 1.6 when we did that separate video for fraction equations. What you do is, if you have just a single fraction on each side, unlike those problems we looked at in the separate 1.6 video where you had bigger fraction equations than that, if there's just a single fraction on each side, you can cross multiply. It's a lot easier. But you cannot have anything outside the fractions when you do that, including a negative sign. So what you need to do is, if you want to cross multiply, again, much easier to do that, put the negative inside of the fractions. And you're allowed to do that here. If you put it inside of either the numerator or denominator, as long as the place that you put it only has a single term, okay, just putting it in there. If it's a positive 1 and you put it in there and it makes it negative, that's perfectly fine. It's still the same fraction. Having a negative on the outside is the same thing as putting the negative on the top. Don't put it in both the top and the bottom, okay, just on the top. But as long as it's just a positive single term up there, like it was before when it was 1, before I moved it in there, then putting it in the numerator there is perfectly fine. It's still going to be the same thing. All right, but now you've got the negative inside, so you just have two single fractions on each side of the equal sign. Okay, nothing outside of them. So now it's okay to cross multiply. 5 times 1 and x times negative 1. Then you divide out, because this is now a linear equation now after you cross multiply. So I'm going to divide out there to get x by itself, and we get x equal to negative 5. Same thing here. X times negative 1. 1 times 4. Divide out, and you get x negative 4. And as I've said before, when you have a fraction equation, check your answers to make sure that the denominators are not 0. Okay, but they're not. If I plug in the negative 5 or the negative 4, it's not going to make the denominator 0. And so, there you go. You don't have to write down the or there, but that's a lot of times how they write it. So we did it. So we solve for u, you guys, and then we back substitute and we solve for x. Don't worry, we'll do a couple more problems here, as you can see, so you'll get used to that more easily. Okay, let's try number 2 now. So I need to solve that. This again looks like another Berry method type of factoring here. 1 times negative 3 is negative 3. I need the two numbers to add up to positive 2 though. 3 and negative 1, they equal negative 3 when you multiply, but they add up to 2 in the middle, don't they? So this is going to work for the Berry method. What do we do? Well, since this is 1u squared, I'm going to do 1u and 1u. Okay. And then I have what? I have plus 3 and minus 1 because I need to put those numbers in there after that. The last step of the Berry method where you factor out the GCFs, you don't need to do that here because the GCF of both of these things, both of these brackets, is equal to 1. And when you factor out 1, it's still the same thing. So nothing happens, and so you could just keep it like this. In other words, if you did that last step, you can do that last step if you want, but it's just not going to change this. And so we might as well just move on to the next thing here. So the Berry method is done. We've got our factoring done as well. Set these things equal to 0 like usual after we're done factoring. We then solve those resulting linear equations by moving over the 3 and moving over the 1, adding the 1 over, subtracting the 3 over. And we got those two answers. But once again, we cannot stop there. If the original variable is x, you need to solve for x. U is just something that helps you get there. Okay, that's why we do this whole u substitution thing. Okay, so what did we do in the last problem after we solved for u and got u by itself? We replaced the u with whatever u was equal to in that problem. Well, in this problem, u is equal to this bracket to the 1/3 power. So what I'm going to do is I'm going to take the u and just simply replace it with that. Okay, let me write that down here. So I'm replacing the u with the bracket to the 1/3 power, just like I did in the last problem with the x negative 1 here. Okay. Now what? Well, doing a little review here on fraction exponents, okay, when you have a bracket taken to the 1/3 power, okay, and then again, this is back in the prereq review packet if you want to look up where it talks about fraction exponents. But when you have something taken to the 1/3 power, that is the same thing, you guys, as when you have the third root of something. Okay, and whatever's taken to the 1/3 power has to go inside the radical. So since this thing is bracketed, that means when it's bracketed, that means this whole thing, not just the -1, but this whole thing in the brackets is taken to the 1/3 power. And so because that whole thing's taken to the 1/3 power, that whole thing has to go inside. Okay, you don't need to keep the bracket there though, because that's the only thing on the inside. Okay, if I put a bracket there, it's going to mean the same thing. But you do need to put that entire thing on the inside. Okay, so if you have a bracket taken to the 1/3 power, that entire bracket needs to go on the inside. Okay, you don't need to keep the bracket once it goes inside, but the whole thing needs to go inside. And it's just like if this was 1/2, then this would be square root. If this had been 1/4, it would be the fourth root. Okay, now that I've done that, okay, and you might be wondering, well, why do we have to convert it to a radical? Well, it just makes it easier that way, because in the last video, we learned that when you have a square root by itself on one side of the equal sign, you square it in order to get rid of the radical, right? Well, wouldn't it make sense that if you had a cube root instead of a square root, that you would cube it? In other words, you got the little 3 to indicate the cube root, and then you put a 3 here. That's going to cancel, just like when you have a square root, the square cancels it. Remember, a square root, it's as if you have a little 2 right here. You don't have to write it down, but it's as if there's an invisible 2 right there. And so the square root and the 2 cancel. In the same way, if there's a 3 right here, the 3 would then cancel everything, and you would just be left with what's in the inside. So let me show you that. Okay, so since this is cube root, we're going to what? We're going to cube both sides of the equation, just like we squared both sides of the equation in that last video. All right, and what do we get? The cube root and the cube cancel each other. You get 2x minus 1. And then this becomes negative 27, because that's what that's equal to. Over here, same thing, but 1 to the third is equal to 1. So once again now, we've now created a couple of linear equations here. Okay, we just had to do it a different way than we did this one over here. But that's what you do when you have something to the 1/3 power here as equal to your u there. So now I move over the 1, since this is linear. Move over the 1 with the negative 27. Divide out the 2. And I get x equal to negative 13. Okay, same idea here. You move over the 1, divide out, and you get x equal to 1. By the way, you do not have to check your answers when I know this is a radical equation, but if you have cube root radicals in your radical equation instead of square root radicals, like in the last video, you don't need to check your answers in that case. You could if you want. It's not going to hurt to do that. But assuming you did all your math correctly here, these are going to end up being true every time if you only have cube root radicals as opposed to square root radicals. So it's optional. You don't have to check in this case. So that is the final answer right there. All right. And lastly here, let's take a look at this last one. If I factor this, I get 8 times 3 is 24 on the Berry method, but I need the two numbers to add up to negative 10. Okay, so the numbers that will work there are negative 4 and negative 6. And since we have 8u squared at the beginning there, we need to do 8u and 8u. Okay, minus 4 and minus 6 need to go in there with it. And then we need to do the last step of the Berry method, just like we did over here, where you got to factor out the GCF out of each bracket. If I factor out the GCF here, which is 4, I get 2u minus 1. If I factor the GCF out of this one, I get 4u minus 3 because the GCF there is 2. Okay. And now we're done factoring that. So we got to set each one of those factors equal to 0 and solve those resulting linear equations. What do we get here? We get, since they're linear, I move over the 1 with the 0, divide out. Once I get the u term by itself, I get u equal to 1/2. And then same idea here, I move over the 3 with the 0, divide out, and I get u equal to 3/4. Okay. Now, what do I need to do now? Again, since u in this particular problem, since u is equal to x minus 4 squared, we're going to replace the u with x minus 4 squared. Just the same idea as the other two problems that we did. Okay. Okay. Now, what happens, you guys, and I know it looks kind of funny because of the fraction there, but what happens when you have a bracket squared by itself, okay, with the variable inside, and then you have no variable on the other side? We learned back in the 1.4 video, let me review that real quick, when you have that situation, bracket with the variable on the inside, exponent 2, no variable on the other side, you do the square root property. That's that thing where you do the 2 square roots here. Okay, one without the negative in front of the radical, one with the negative in front of the radical. You get rid of the square here, and it's just you bring down the inside of the bracket twice. And then you solve for the variable after that. Okay, let's try that. So I take, and we got to do it twice because there's 2 different ones. So there's going to be a total of 4 equations here. Okay, so we're going to get x minus 4 is equal to square root of 1/2, x minus 4, and I'll zoom in here. It's going to get a little bit tight here. -1 square root of 1/2. So that's for the first one. That's for this one right here. Okay. And then this one here is going to be x minus 4 square root of 3/4. X minus 4 equal to negative square root of 3/4. Okay. And so this is going to look similar to problem number 6 from the 1.4 video we did, okay, where you've got x, then a constant term here, and then you've got this, radical with a fraction inside of it. Just want to give you a visual of what another problem would look like if it was similar. Notice I moved over the term, just like we learned how to do in that section to get the x by itself. Okay, let's see how that works out here. So we need to move over the 4, right? So if we do that, we end up getting x is equal to, let me just write this down first here. We're going to get x is equal to 4 plus the square root of 1/2, and x is equal to 4 minus the square root of 1/2. But we learned what? We learned that that's the same thing as saying 4 plus or minus the square root of 1/2, because the two answers are the same. 4 plus square root, 4 minus square root. They're the same except for you have a plus in the middle of the first answer and a minus in the middle of the second one. Since the other parts are the same, you can just change that to plus or minus to consolidate it down into one statement right there. Same thing happens over here. Okay. And we get what here? We get 4 plus the radical. And we get 4 minus that same radical, and so that comes out to 4 plus or minus the square root of 3/4. Okay. And so that's actually a total of 4 answers there. Because remember, when you have a plus or minus, that's 2 answers by itself. So there's 2 answers here. There's 2 more answers here for a total of 4. Okay. By the way, you could take this one step further, but it's optional, as I mentioned back in 1.4. Okay. You could take this radical and split it apart and then add it to the 40. You don't have to do that. That's optional. It's just something that the textbook oftentimes does when it puts its answers in the back of the book for you to look at. But you can leave it like this, okay? That's okay. The important thing is you got x by itself there. The radical can have the fraction side. I'm fine with that right now. Okay, so that concludes this section here. Okay, again, the key thing is use your u, solve for u, and then back substitute what u was originally equal to. Remember, you have to solve for the original variable x in the end. Okay, so let me know if you have any questions about this. You have a good day and take care, and we'll see you back in the next video for section 1.7.